Hello everyone. Today, I am honored to present our work entitled a 3D-FSS-Based and Front-Feeding Shared-Aperture Base Station Antenna for 5G Mobile Communications. This work primarily focuses on suppressing scattering interference and common mode interference between adjacent frequency bands. First, we investigated the parameter tuning mechanism of the FSS unit to suppress scattering interference. When we only varied the patch size inside the FSS unit, we observed the transmission coefficients at 0 degrees, 20 degrees, and 40 degrees incidence. The results showed that while the passband shifted to the left transmission 0 remained almost unchanged. Therefore, we conclude that only changing the patch size within the dipole will only affect the 0 points on the right side of the passband. In contrast, when we varied the unit cell size, we found that as the unit length increased, we observed the transmission coefficients at 0 degrees, 20 degrees, and 40 degrees incidence. The left transmission 0 shifted leftward, accompanied by a wider passband. Therefore, we conclude that changing the length of the dipole arms will affect the left 0 point of the passband. This discovery indicates that the internal patch size and the dipole arm length can independently control the right and left boundaries of the passband, respectively. Based on these findings, we developed an evolution strategy from Case 1 to Case 4. Case 1 is a basic dipole structure, equivalent to an LC series circuit, exhibiting bandstop characteristics. Case 2 introduces a rectangular patch to achieve independent control of the right 0. Case 3 innovatively incorporates a 3D choking structure, which increases the transmission electrical length and shifts the left 0 leftward. Finally, Case 4 seamlessly integrates the rectangular patch with the 3D choke, enabling simultaneous control of both left and right transmission zeros without increasing the antenna footprint, achieving the target passband of 2.7 to 3.4 GHz. Theoretical derivation confirms that in both Case 1 and Case 3, simply increasing the transmission electrical length shifts the resonant 0 to the left. The 3D choke achieves this by adding shorting posts on the dipole arms. This design precisely realizes electromagnetic transparency in the target band without expanding the antenna area, as follow experiment. In our experiments, we adopted a stacked configuration of low-band and high-band antennas. As can be observed, when the dipole arms of the low-band antenna are constrained, only with the 3D-FSS scheme applied to the low-band antenna can the gain and beamwidth of the high-band antenna be restored to levels nearly identical to those when it is placed in isolation. Having addressed scattering interference, when we integrate the high-band and low-band antennas into a 1x4 array, with the high-band antenna fed by a Wilkinson power divider and the low-band antenna fed by a coaxial cable, strong common mode interference is induced in the high-band antenna when the low-band antenna is excited, as illustrated by the electric field distributions at 2.1 GHz and 2.3 GHz shown in the figure. Conventional balun feeding causes coupled currents to form loops on the radiating surface, generating strong common mode interference and severely distorting the radiation pattern. To solve this, we propose a novel front feeding structure. Without any additional coupling layers, this design completely eliminates common mode interference simply by changing the feeding method. The core principle is inspired by bandstop filter design. Energy coupled from the low-band element to the high-band element splits into two paths. One path couples through the substrate to the backside ground. The other flows through a specially designed shorting line directly to the backside ground. The shorting line length is set to 1/4 wavelength at the target frequency of 2 GHz, forming an overall third-order bandstop filter that effectively blocks common mode coupling currents. As can be seen, when the low-band antenna is excited, the common mode currents generated in the high-band antenna are almost entirely suppressed within the bandstop filter structure, thereby almost completely eliminating the common mode interference. Both simulation and measurement results confirm that the front feeding structure improves the low-band gain by an average of 1.1 dB, while maintaining excellent impedance matching. We assembled a 1x4 array consisting of 1 low-band element and 4 high-band elements for testing. The measured results demonstrate low-band gain, 8.3 plus or minus 0.5 dB. High-band gain, 13 plus or minus 0.7 dB. Port isolation between low and high-band elements, better than 20 dB. Cross-polarization, better than 25 dB. Stable radiation patterns, meeting 5G base station antenna requirements. Compared with existing solutions, our design achieves compact integration of adjacent frequency bands while maintaining a low profile, significantly improving spatial utilization efficiency. The main contributions of this paper are as follows. A novel dual bandwidth, dual polarization staggered shared aperture base station antenna, unit cell, is designed, featuring closely spaced operating frequency bands. This design eliminates the need for additional baffles to achieve high port isolation and resolve coupling issues. The implementation of 3D-FSS effectively addresses scattering interference when the frequency bands of the antennas are very close, adjacent frequency. Such low profile and proximity of elements within the unit cell are firstly addressed and operate in adjacent frequency. The front-feeding structure effectively mitigates common mode interference without increasing the area occupied by the antenna and without necessitating complex manufacturing processes, which helps to reduce costs. Thank you for your attention.